SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Advanced Thermodynamics and Combustions, Module 8, Combustion and Flames. Till this point of time, we covered 4 lectures on laminar premixed flame, laminar diffusion flame, droplet evaporation and droplet burning. Today, we are going to focus on the last lecture of this module, that is engine combustion and pollution. Till this point of time, we have covered all the basic aspects of theoretical backgrounds and mathematical modeling of combustions, and in this lecture we will try to focus on application part. Number 1. Number 2, also we will look into the pollution levels or pollutions that comes out after the engine combustions. And if pollution has come out, then what is the criteria of its quantifications. So, these things will be the focal point of our discussion today. So, on this lecture number 32, that is engine combustion and pollutions, we will discuss about the combustion phenomena in petrol engines, diesel engines, gas turbine engines and rocket engines. And all these things will be just a preliminary conceptual thoughts how this combustion phenomena happens. Subsequently, till this point of time, whatever methodology or mode of combustions we have looked into, we will try to put a glimpse that how those concepts can be utilized in these engine combustions. And towards the last part of our discussions, we will discuss about pollutant emissions and how to quantify these emissions. And one of the important aspects which was supposed to be in this combustion course, that was turbulent flames, but due to lack of time we will not be able to cover this, but rather I will just put an introductory remarks on this turbulent flames towards the end of this lecture. So, let us start the first thing, the combustion in petrol engines. We all know that we all know about the basic UG course, which is combustion in SI engines, spark ignition engines, where the combustion phenomena is mostly viewed that fuel and air mixtures enters into the engine cylinders, and towards the end of the compression stroke, the spark plug ignites the charge, and as a result the combustion happens. This was the thought we put when you discuss in the IC engine course. Now, I will just add or something further, that and to whatever discussions we have made so far, this particular nature of combustions falls as the pre-mixed combustions, where the pre-mixed air and fuel combustions happens is prepared locally, and it is a homogeneous mixtures, and when it enters, spark gets generated, or we ignite the fuel through a spark, and through this we generate a flame front, and this flame front propagates into in the combustion space. What we can see is that if you can just typically view, this is the combustion zone. We can think about many number of layers, 1, 2, 3, 4, like these zones. Now, when the at the beginning of and in this entire zone, we have this homogeneous fuel and air mixture. Now, when the spark is ignited, the zone 1 gets affected. So, a flame front is initiated, and slowly this flame front moves to the zone 2, zone 3, zone 4, and as and when it propagates into the different zone, we can see that zone 1 would be, once it completes the zone 1 will be full of combustion products, whereas zone 2, 3, 4 and there are not, combustion has not been attempted or has not started. And subsequently, when the flame front moves through these zones, it keeps on igniting the subsequent fuels. As a result, entire cylinder space is covered with the complete combustion products. And this combustion process can be thought of three major regions. One is ignition and flame developments, and here this ignition happens through a spark plug, because it creates an electric discharge. Then during the flame propagation phase, almost 80 to 90% of the charge is burnt, and because of this we find a sudden rise in the pressures. And towards the flame termination, that means when the combustion the flame plant reaches to the last zone, only 5% of charge is burnt, and that is viewed as the drop in pressures. Now, if you look at the pressure and crank angle diagrams or the subsequently pressure time diagram, we can see that at one particular location of the crank angle, ignition happens, and it starts with a slow rise in the pressures and followed by a sudden rise in pressures. And when the flame front is in the termination mode, the pressure peak drops down, and we'll see that towards the expansion stroke the pressure drops. Another important phenomena in the spark ignition engine is the knocking. So, what could have happened is that during a normal combustion process, if it happens, if the flame plant which is initiated through this in the zone 1 subsequently burns the charge in the different zones, then we will have a normal combustions. And due to variety of reasons, if there is some rise in the pressures or rise in the temperature, due to some regions in the zone 3 or 4, not due to flame front, rather due to self ignitions, then we can think about some kind of disturbances in the pressure pulse, and those disturbances are typically called as knock. So, in a normal combustion phenomena, the trace of the pressure time diagram is a smooth, and whereas with a knocking situations we will find towards the expansion stroke there is a kind of oscillations that drops in towards the end phase of the combustions. So, what we can say is that knocking, if at all has to happen, it is very likely that zone 4 is the most affected zone, or we can say zone 4 is the locations at which we can expect a self ignition due to knocking and as a result of knocking. Then we will move to combustion in the diesel engines. We all know that when diesel engines are governed with Otto cycles, and it is a constant pressure based combustions, and here instead of the pre-mixed air fuel mixture, we normally do that air is compressed within the engine cylinders, and fuel is injected into this chamber through an injection process. And we all know in our earlier discussions that we have seen two important concepts. One is diffusion flame, other is droplet combustions. First thing is that when a fuel jet comes through the injectors, it forms a flame jet. As you can see here, it is a diffusion flame jet. And when we have a constant density mode, we have analyzed one thing, that fuel jet injected into a quiescent air. Same thing we can view here, that when it is injected, it is in the liquid form, and when it forms, it sees a medium where it is already peak, it sees a medium with heated air. So, this fuel liquid droplets gets vaporized by seeing this environments. So, in this case what happens, the fuel gets injected from an injector, and it when it comes out from the injector, it sees an ambience which is a compressed air at elevated pressure and temperatures. So, as a result, the self ignition will occur. Now, such self ignition process is modeled through a layer of diffusion sheets. So, here we can say that there are different zone A, B, C, D, E. So, A can be considered as a too rich to burn, B can be considered a rich but combustible, C can be considered as a stoichiometric, that means fuel and air has on this flame sheet, it is stoichiometric combustion happens. D is lean but combustible, and E is too lean to burn. So, all these things the different zone happens here. Now, such a things if has to be modeled through a diffusion sheet model, then we can say on this particular flame sheet one situation could be the fuel air is in the stoichiometric proportions, and within this flame sheet we may have combination of fuel as well as products, and outside these things we may have combination of oxidizer and products, because it is a lean mixture. So, I just try to correlate this fact that same thing happens, that is two important phenomena, one is through flame sheet, other is that droplet combustion, that means liquid droplets that comes through the injector, it gets vaporized. So, and we can and in fact there are the droplets have certain lifetimes, and these subsequent droplets gets created, and they also after that they also dies down after the lifetime is over, and entire phenomena that happens only in a few millisecond durations. And of course, when you look at specifically in the diesel engines, there are different ways that fuel injection can take place. One is indirect injection, other is direct injections. So, in a indirect injection what happens, the fuel is injected under high pressure into the pre-combustion chamber, the fuel droplets begin to evaporate and fuel vapor mixes with air in the chamber, and some portion of the fuel and air mixture auto ignite, and this initiate a non premixed combustions, and because of this heat release, pressure rises in the pre-combustion chamber, and subsequently the partially reacted fuel air mixture and the remaining fuel droplets mix with additional air in the main chamber to complete the burning process. The other category of the injection systems is the direct injection systems. So, recent advantage is that instead of looking for this earlier version pre-combustion chamber, we can think of the injecting the fuel through a multi-hole fuel injector systems, because it is a quite efficient process in the burning of the fuel. And in this process what happens, the fuel air mixture is governed by the process injection process as well as the air motion within the combustion space. So, here the combustion phenomena is viewed as pre-mixed as well as the diffusion control mode. And we all know that diesel fuels are less volatile than the SI engine fuels, because they readily auto ignite. So, the rate at which the fuel vaporizes and mixes with air at par with the rate of reaction leading to the auto ignitions. Then other important aspect is that the fuel when the first fuel is injected into the chamber, then before it is subjected to an ignition source. So, when you talk about the ignition source, it means that so in the entire combustion space there are some pockets or zones where it is expected that fuel can be auto ignited, and slowly once that auto ignition takes place, the flame front generated at that point, and subsequently with that zone the information is transferred to the other zones, or the flame propagates to the other zones, and side by side there are also parallelly fuels that is subsequently injected. So, the entire process is governed through a diffusion mode, since the ignition source which is a pre-existing flame is present when the fuel is injected. The droplet evaporation and burning are also important for direct and indirect engines. So, here when you think about the mode of combustions, we can bring the concept of droplet evaporation and burning. The moving to next type of combustions that we normally do in gas turbine engines. These gas turbine engines are usually employed in the aircrafts. So, here also it is similar concept as that of diesel engines, but with a different philosophy or different technology. So, if you look at the particular figure that talks about the schematic of annular turbine, which consists of a diffuser as well as nozzles, or it is basically an annular section, and in this annular section entire combustion process is modeled. So, if you look at this combustor, it has three different zones. One is primary zone, secondary zone and dilution zone. So, air that comes into the system, that means compressed air from the compressor unit comes into the combustor, and in these combustions we have fuel nozzles, and typically they are incorporated in the primary zones. So, the fuel is injected to into the air, and at side by side the air motion, that means speed of the air is also very high. Side by side the mixing takes place. So, and in fact this is one such nozzle. There are multiple nozzles, that means the fuel is injected into air at multiple locations of this annular space. So, as a result this mixing takes place, and during this process already it is a heated temperatures. So, we can say that they are atomized within the annular section of the combustor. Of course, to have the sustained combustions, we can do a swirling actions or recirculation zones which is created within this annular portions to have a stabilized flame. And the pre-mixed combustion is generally achieved by vaporizing the fuel and mixing with air before the mixture enters into the hot combustion zone, where it ignites and burns. Now, this is what happens in the primary zone, and subsequently when it comes to the secondary zones, that means in the entire combustor, there are different zones, and these different zones have different purposes, because when the sustained flame gets initiated in the primary zone and it moves to through these annular sections, then we expect that a regulated tailored flame has to be generated when it enters into the turbines, because at that point the entire combustion products has to happen. Now, to have those things, the secondary zone or dilution zones have a important role. So, what does they do is that side by side in the secondary zones we also supply fuel and also the mixing or swirling actions, such that when it enters we get a stabilized combustion or the flame gets stabilized. There is a concept called liner cooling flow. So, what does this mean is that if you look at the another view of the sections, so this one particular section, so if you can see these arrow lines, these are nothing but airs, and this is the air flow, arrow lines refers to the air flow, and these are the holes which are kept in the primary zone, secondary zone, and maybe the dilution zone. And what we have is that in addition to this primary air, we also have a secondary air that comes from these compressors, and they call this as a liner cooling. Now, this liner cooling is required because what happens is that we expect a particular temperature distributions towards at the end of the combustion. That means, when the flame is about to enter into the turbines, we expect the flame temperature distributions along the radial direction in such a way that the turbine gets the minimal thermal stress. So, to have this, we require this liner coolings. So, what do we mean by this minimal stress? Means that is where the role of dilution zone comes into pictures. What we expect is that if you look at turbine viewpoint, turbine normally faces the highest temperature in a gas turbine engines, and because of these high temperatures or hotspot gases, they can damage the turbine blades. So, in order to reduce this thermal endurance, we expect that there has to be a particular temperature distributions across the turbine blades. And what we expect is that the gas turbine temperature has to be tailored to increase it from blade root through a maximum, then decrease at the tip. So, the temperature profile has to be tailored in such a way that it should increase first, again then while it reaches to the blade tip, the temperature should fall down. So, there the role of dilution zone comes into pictures, and through this dilution zone we tailored the frame or give a particular temperature distribution pattern to the flame such that the thermal endurance at the turbine blades gets minimized. And such a temperature distribution pattern for the gas turbine combustor outlet is known as pattern factor. Normally, what type of temperature distribution we require at the end of the combustor is nothing but your pattern factor that has to be taken into account while doing this. And for this, the dilution zones, normally it is a kind of a cooling effect that is produced for the flame to quench, and subsequently entire combustion products has to expand. So, this is a different part of discussions. So, this particular concept talks about the gas turbine combustion. The next part, or when you travel faster, the gas combustion will not happen. We require some kind of other technology where we should avoid the use of mechanical devices. Rather, we expect that some the phenomena through shock waves or shock assisted combustion comes into pictures. So, what happens is that when you travel faster, it is faster, number one, and when you going to very high altitudes, there is a lack of oxygen or oxidizers. So, the rocket engines normally carry fuel and oxidizers in separate tanks, and these fuel and oxidizers are normally the liquid, typically liquid hydrogen and liquid oxygen, and the concentration in liquid is done because they have large energy density as compared to the gas phase mode. And there are two types of combustor. One is pressure fed type, other is pump fed type. What happens if you look at this particular figure, we have a high pressure gas, and this high pressure gas pressurizes the fuel and oxidizer tank through this propellant valve. As a result, the fuel is injected into the thrust chamber. Whereas in a pump feed type, we do not have this high pressure gas medium, rather we have two different pumps that that gives necessary pressures for this propellant valve to inject the fuel into the combustion zone. The thrust of the engine is produced by creating hot high pressure gas from the combustion of fuel and oxidizer in the combustion chamber. The flow is subsequently accelerated through the supersonic diverging nozzles. In fact, the type of combustion that is going to happen is, one is droplet, because it's a droplet kind of combustions. And here also we can think premix and diffusion burning, which is likely to happen in a rocket combustion mode. Another important aspect is that when you think about rocket combustions, the subsonic combustions is normally referred as ramjet combustions, and supersonic combustions are referred as ramjet combustions. So, these are different terminology that are used in the rocket engines. The next important aspect that we are going to discuss is the pollutant emissions. In fact, the control of pollutant emissions is a major factor in the design of modern combustion systems, because the primary air that are emitted directly from the source via many chemical reactions affect the atmospheres. So, when such reaction takes place, they affect environment as well as the human health in many ways. First is altered properties of the atmosphere, because this combustion phenomena changes the atmospheric air quality. They are harmful for vegetations. They also damage soils and of course deteriorate the materials, and there is a potential increase in the sickness and mortality of the human beings. So, these are the kind of societal loss due to the pollutions. Now, typically in the engine combustions, the type of pollutants are, first thing is particulate matter. So, particulate matters comes as a soot particles, fly ash, metal fumes, aerosols that we can see in the atmosphere. Then we have sulfur dioxide either in the form of SO2 and SO3. Then we may have unburnt or partially burnt hydrocarbons. Then we can have oxides of nitrogen, NOx, typically NO2 or NO. We may have carbon monoxides. Then greenhouse gases, they are N2O and CO2. So, all these things are the culprits for the human civilization. So, the origins of all these things are nothing but the premixed combustion and non-premixed combustions. Other possibilities could be we do not operate the combustion through a non-stoichiometric mode, or normally the combustion processes are occur through non-stoichiometric mode or dissociation of nitrogen and impurities in the fuel and air. Now, let us see how those pollutant emissions are affecting the human life and the atmosphere. The undesirable emissions generated during a combustion process of automobiles and IC engines pollute the environment, and they contribute to global warming, acid rains, smog, odor, respiratory and health issues. Now, one of the major concern of the pollutants is in the troposphere, and this troposphere is nothing but the lowest layer of the atmosphere. And what happens there? The emission of NOx, and when you talk about the civil transport aircrafts, so when they at lower altitudes, normally they travel at 30,000 feet altitude. So, at that locations the question of emission of NOx becomes a vital factor. What happens there is that if you look at atmosphere, we have it is covered with ozone layer, and these ozone layers protect the sunlights. So, various wavelength forms of the sunlight gets protected through the ozone layer, and they do not come back to the earth's surface. And but what this pollution does is that these pollutions creates or breaks that ozone layer. How? That is known as catalytic destructions. The catalytic destruction of stratospheric air ozone is through the formation of NO in the reaction mechanism has a deadly consequences. The removal of ozone from the stratosphere allows harmful ultraviolet solar radiations to penetrate into earth atmosphere. How? First thing is that when you have this NO formations, when it reacts with O3, it gives NO2 and O2. This NO2 again mix with O, it gives NO plus O2. Now again this NO2, when it gets energy from the sunlight, it forms NO plus O. So in odd words means NO and O, they act as a catalyst. Every time those things are there, it keeps on forming NO, and because of this NO, O3 it breaks the ozone layer O3, because NO only reacts with an O3 to form O2. So because of this reason, we can say the ozone is destroyed first by reaction NO, while NO is again regenerated in the second reactions. And another important aspect is that monoatomic oxygen is highly reactive. So it initiates many reactions. One of them is the ozone formation at the ground level as well, and which is harmful for lungs and biological tissues. Ozone, although it protects the sunlight, but at the ground level the ozone has a harmful effect for the human bodies. So these are the side effects of the pollutants. Now let us see how you can quantify the emissions. So one way to look at the emissions is representing as a emission index. The emission index for any species which is formed due to combustion, if you denote that I, is the ratio of mass of the species to the mass of the fuel burnt by the combustion process. In particular, this emission index EI is a dimensionless quantity, but we typically represent like grams per kg of fuels, so that we can quantify in a proper manner. This EI expresses the amount of pollutant that is formed per unit mass of the fuel and independent of any dilution of the product streams or efficiency of the combustion process. And this EI can be treated as the measure of efficiency of a particular combustion process in producing a particular pollutants. The combustion hydrocarbons of fuels in air is determined through the concentration or mole fraction measurements, assuming the fuel carbon appears as a CO2 or CO. So one way to look at is define the term emission index EI for the species I, mass of the species I which is emitted to the kg of the fuel burnt. Now such things, if you want to express in the molar form, we can say that particular the parameter of interest is either CO2 or CO, and we have to normalize the species I with respect to CO and CO2, and if each of them we can find out through these chemical reactions, and here X is the mole fraction of MW stands for the molecular weight. So these are the by definitions. Other way of to quantify these emissions, normally the emission analysis is done through a gas analyzer. We take a strip of gas or certain quantity of the gas at the end of the combustion pipe. So taking that sample, we try to measure. Now if you look at particular combustion equations for a hydrocarbon fuel, if you say CXHY is a fuel and it mixes with air with a quantity of oxygen and 3.76 a quantity of nitrogen, then it gives CO2. Ideally it should give CO2, H2O, O2, N2, and there are some stress species, and these stress species could be formation of CO, NO, depending on the nature of the mixture, they can be like this. Now here the one important point is that whatever trace species that appears in these reactions, that can be controlled through the quantity B, means that can be linked or that can be correlated the equivalent quantity of oxygens through the parameter B. So, for that reasons we say that we define a parameter called as a concentration corrected to particular level of O2 in the product stream. That is typically referred in the literatures to have a kind of a proper comparisons. And these corrected concentrations is either represented as a wet basis or dry basis. Now, to represent dry basis, what you say that if you look at reactions, so if suppose if you want to calculate on dry basis, the concentration of Xi and dry will be Ni, that is number of moles of species I divided by N mixture dry. Now, when the total mixture number of moles for the mixture needs to be calculated, then this H2O has to be ignored. Now, when you calculate with respect to weight, the H2O has to be included. That means, the coefficients of H2O, that is Y by 2, has to be included in the total number of moles. I am not going into details. So, once you take the balancing, different formulations can be made like N mixture by N dry and N mixture weight by N by dry. We can frame the Xi as a ratio of these dry to wet combinations. Another way of looking at that, let us take that when we are measuring the emissions through gas analyzers, we are measuring at certain level of level 1. So, in the level 1 we are measuring some O2 and this things has to be corrected to another level O2, which means that if I change the or if I control the combustion parameters so that we can get another level O2, then what would be the concentration of this species. So, basically distress species regulations can be controlled through an appropriate measure related to the oxygen concentrations. So, these things a simple algebraic simple equations can be formed for this for a particular trace species I with respect to its concentration at level 2 and level 1, and they can be correlated with respect to mixtures of oxygen at level 1 and level 2. So, these things will explain when you solve the problem. Solve a numerical problem towards the end of this class, we will explain more details onto this. So, this is all about the quantification of emissions, and there are some other methods which are typically called as mass specific emission MSE, which is defined in terms of emission index and brake power, and also we have specific emissions defined in terms of fuel energy, that is enthalpy of combustions and emission index. So, different philosophies or different applications require the quantification of emissions in a different perspectives. This is all about the content. Now, I am going to the last segment, that is which was supposed to be the part of this course, but due to the lack of time and lack of the nature of the course, it is very difficult to follow this turbulent flames, but rather I will just end this combustion with an introduction to turbulence flames. So, in the combustion mode we discussed premixed combustion, non-premixed combustions, laminar premixed flame, diffusion flames, droplet combustions, droplet burning, all these concepts we have introduced. What we have not covered, and also to some extent we try to see how they can be mathematically modeled. By looking at these equations, we can make a judgment that when we go when you bring more number of equations, the complicacy becomes tremendous. I mean, it is very significant complication happens. This is exactly what happens in a turbulent flow situations. Typically same concept, that is pre-mixed combustion and non-pre-mixed combustion can be equally applicable, but due to the nature of equations, we will land up having a complicated equations, and those equations is almost difficult to solve. To give my final notes on these turbulent combustions, I can say many applications require turbulent flames for self-sustained combustions. The turbulent combustions can have pre-mixed flame as well as non-pre-mixed flame. The pre-mixed flame is combustion is modeled by three distinct zones. One is laminar flame zone, flamelets eddies regime, and distributed reaction zones, whereas non-premixed flames are normally modeled through the simple jet flames. The flame stabilization of premixed turbulent combustion is generally achieved by incorporating pores, blob bodies, and area change processes. We can have swirling flames that are often introduced in the practical devices for non-premixed turbulent combustion, and it emphasizes recirculation zones for flame stabilization and shortening the flame length. The characteristics flame time, characteristics chemical times, fast chemistry are some of the important features for the turbulent combustions, and because of this reason there is a tremendous complexity which is involved in mass, species and energy conservation equations with fast chemical kinetics reaction mechanisms. So, this I leave it to the research space that individuals can look into, and of course, the final note I can say, of course, that there is not a definite solutions for a given applications, and many times the empirical correlations are relied upon for realistic estimates. The last part I will try to solve a numerical problem which is based on the quantification of emissions. The problem statement says that in an engine test which uses iso-octane fuel, we measure the exhaust products by volume on dry basis, and they are CO2, CO, O2, NO, C2H4 equivalent. That means, these are the trace species which need to find out, and they are nothing but the C6H14 equivalent, and we need to we need to find out the emission index of unburnt hydrocarbons. So, instead of unburnt hydrocarbons, we have introduced C6H14 or hexane equivalent. So, to do this, first thing that we have to recall that what is the definition of emission index. So, EI instead of I, subscript I, we are writing C6H14, that is equivalent to, by definition we write C6H14 divided by concentration of CO plus concentration of CO2, this is multiplied by X time molecular weight of species. So, C species is C6H14 hexane divided by molecular weight of fuel. So, fuel in our case is C8H18. So, here we say fuel as iso-octane, and that is C18H18, its molecular weight is 114 kg by kg mole. And when you talk about hydrocarbon, and this is hexane equivalent, that is C6H14, its molecular weight is 86 kg per kg mole. Now, what is X? X is a number of moles of carbon per mole of fuel. So, we have 1 mole of fuel will contain 1 mole of fuel C18H18 contains number of carbon as 8. So, we can say X is equal to 8. And what data has been given? The concentration of XCO. XCO is given as 0.1%, that is 0.001. XCO2 is given as 12.5%, that is 0.125. So, we have all the values here. Now, inserting the value, then we can estimate EI emission index with hexane equivalent C6H14 as 0.0172 kg by kg of fuel, and ideally we write it as 17 gram per kg of fuel, which means if you take 1 kg of isooctane, that is C18H18, it will give you 17.5 grams of unburnt hydrocarbons equivalent to hexane. So, this is what it means. Next thing, for the same problem, we are going to find out NO concentration on weight basis, and for this problem we have to recall the conversion of dry concentration to wet concentrations. So, for that things we have to recall the expressions X NO wet is nothing but X NO dry, then N mixture dry divided by N mixture wet. So, we have fuel C8H18, where we can say X is equal to 8, Y is equal to 14. So, if you say CXHY, Y will be 18. So, this is fuel, and this ratio N mixture weight divided by N mixture dry has this relation, that is 1 plus Y by 2 into 4.76 A minus Y by 4. Now, in this case we need to find out what is A, because we all know Y. So, what is A? A is defined as X plus 1 minus XiO2 dry, because we are finding out dry first, into Y by 4 divided by 1 minus 4.76 XiO2 dry, because the data what gives is on dry basis. So, XO2 is given as 2%, that is 0.02. So, accordingly we can find out A as 13.7. We know X, we know Y, we know Xi, O2 dry. So, A is 13.7. Then this ratio can now be found out with knowledge of Y and A. This ratio is 1.148. Now, once you know this 1.148. So, XNO weight would be XNO dry is 76 ppm divided by 1.148, because this is the other way. So, XNO weight can be calculated as 66.2 ppm. What we see is NO concentration in wet form is less than the NO concentration in dry form. So, this is the problem demonstrate how you need to compare the wet concentration and dry concentrations. The last part of the problem where we are trying to correlate the two different streams of exhaust streams with different concentration of O2. So, in the stream 1 in the level 1 we have concentration of O2 as 2%, in the level 2 we need to have concentration of O2 as 5%. So, how these two concentration regulates the NO measurements, this is the things that we need to address. Now, for this problem we almost have this data which are available with us. So, we have to use two expressions NOx mixture dry and mixture wet expressions, and for this we can say N mixture xy O2 concentration, that can be found out from these expressions. So, we have 4.76 x in this case is 8 because C8H18 in plus 1 minus XO2 dry, XO2 dry is 0.02, y is 18, x is 8. So, it is 18 by 4 divided by 1 minus 4.76 xy O2 is 0.02. So, this and minus 18 by 4. So, this X2 concentration at level 1 we get 60.8. This is at 2% concentration. Now, similarly, we can find out N mixture xy O2 at 5% O2 concentrations, where we need to replace X xy O2 as 0.05. So, this will give you the value as, this will imply it will be 4.76 into 8 plus 1 minus 0.05, instead of 0.2 we are writing 0.05. So, 18 by 4 divided by 1 minus 4.76 into 0.05, and this minus 18 by 4 which will give you this number as 72.2. So, we have two numbers, one is this number, other is that number. Data that is given Xi current at level 1, is 76, NO concentration at level 1 is 76. So, we can say X NO at level 2 would be X NO at level 1, that is 76 ppm into at level 1 this value at equivalent value of mixture at O2 at level 1 is 60.8 divided by 72.2. So, this number is 64 ppm. So, what it says is that by regulating the oxygen concentration to 5%, we can see that NO concentration drastically reduces. So, in other words, we can control our unburnt mixture in such a way, so that we can regulate the oxygen concentration to 5%. So, if you that means you have on dry basis, when the oxygen concentration increases from 2 to 5%, you can see NO concentration reduces from 76 ppm to 64 ppm. This is what the idea for reducing the pollutants from the during a combustion process by regulating the oxygen concentrations, and that is where the importance of this expression is realized. So, with this I conclude this particular lecture, this particular module. Until date we have completed all the modules, and thank you for your attentions. I hope you have enjoyed all the modules, and best wishes and best of luck for your future career. Thank you.